Hi, welcome to XMaths. My name's Lee, and today we're going to work on our logarithms again, and in particular on log equations, having dealt with the simplification last time. And then we're going to go back and we're going to visit graphs again, and we're going to remind ourselves about the log and the exponential graph, and of course that would involve inverses. So actually it's pulling it all together into one section, which is always fun to do. Right, let's quickly remind ourselves of our log definition. Our log definition said the following. It said if I have log to the base a of b equals c, then a to the c equals b. So in other words, that base brings that exponent up to give me that value. And if you remember from last time, we talked about the various restrictions that would apply. We said that a would not equal 1. Obviously, if that was a 1, 1 to anything is 1, so it's a pretty pointless case. And a would be greater than 0. In other words, this thing can't be a negative, because if it was even or odd, it would depend if it's positive or negative. So we don't want that kind of situation. We want it to behave well. And so actually what we're doing here is we are looking at only a greater than 0. Right, over here we have our value b. And we said that that b would always be greater than 0. Now again, that makes sense. If this is greater than 0, then this answer here has to be greater than 0. The only way for that to be a negative is for this to have been a negative. And then, of course, the c value, well, the good news is the c can be absolutely anything. It can be a fraction, it can be a decimal, it can be absolutely anything. So there is no restriction on the c. Now, why am I stressing this? I'm stressing this because when we're dealing with our equations, we always have to take into account that those were restrictions on our particular definition. Of course, this works backwards as well. So if I know that's an exponent, I can bring it back to a log. Right, just to recap a little further, let's remind ourselves about our laws. Just the most important ones. We know that if we have log to the base m of a added to log to the base m of b, it actually means the log to the base m of ab. Likewise, if we have log to the base m of a minus log to the base m of b, then it actually means log to the base m of a over b. Third law says if we have log to the base m, well, let's say n times log to the base m of a, it's going to be log to the base m of a to the n. Right, now at the end of the laws, we also have our deductions. And those are quite useful when we're working here. And the first one says log to the base a of a is 1. And the second one that's very useful is log to the base a of 1 is 0. We might need others, but I think that's good enough for now, just to recap for ourselves how this is done. So remember the definition, in particular the restrictions, the 3 laws. There is a 4th law, but we don't really need this one at the moment. So those 4, remember adding means timesing. It sounds really strange. Subtracting logs means dividing the numbers, and multiplying implies raising to a power. And then the 2 deductions that we have over there. Right, let's move to the first question. Now, this question is taking the form of a traditional definition as such. So let's put the definition next to the question, and that'll help me to get a direction on how to handle it. The question says solve for x. Now remember, we said just now log to the base a of b equals c implies that a to the c equals b. Now if we look at this, the only problem I have is this number here. That number is problematic, so we're going to get rid of it before we even start. So we're going to go log to the base 2. Notice I tuck my base underneath the g's tail, so I don't get confused over what is the base and what is the actual number. I'm dividing by 3 on both sides, so this is going to become 4. Now, it definitely takes this format. So at this stage, I can say therefore, now notice I don't use an equal sign. The reason I don't use the equal sign is I would have two equals on the same line, and that is really not a good idea in mathematics ever. So rather go therefore if you feel you must write something, or thus write the word, whatever. But don't put two equals on the same line. Right, so over here we go, and we're going to say that base is 2 to the exponent 4 equals x minus 1. So that base 2 takes that exponent, which equals that there. Another way to think of it is that 2 kicks up that 4 to give me the x minus 1. Right, so 2 to the 4 is a nice number. It's actually 16 equals x minus 1. And now we're going to solve for x, so we're going to move this 1 to this side, so it becomes 16 plus 1. And so x is equal to 17. Now, remember what I said to you. I said it's very important that we remember the restrictions on our logs. Because if we get an answer that's going to cause a problem with one of those restrictions, then we have to disregard that answer. So let's have a look and see if that's going to be the case here. Well, what do we know? The base is 2, so we have no problems with our base. But we also know that this thing here, this x minus 1, has to be greater than 0, which means the x value has to be greater than 1. If I look, there is 17 greater than 1. Most certainly it is, so there's no problem. Another way to handle it is just to take it back here and say, okay, if I put the 17 in there, I would get 16. Would that cause a problem? No, it wouldn't, so I don't have a problem. But the more mathematical approach would be to do that. I personally think it's better for you, certainly with the level of logs we're doing at school, to just go and substitute in and make sure that you're not causing any problems according to my definition of a log. Right, so that's the first way we get asked to work with these equations. Let's look at another question. In the second question, it says solve for x, and it gives me that statement. Now, again, if you look at it, if we're going back to that definition we had that looked like this, you can see that the format you're looking at here is not correct. However, we have a plus sign. And from our laws, we know that plus in logs means multiply the numbers. So in other words, I could go log to the base 3 of 8 times x plus 2 equals 2. Now at this stage I can multiply this in, or I could just leave it like this, but let's multiply it in so it makes it look more coherent. So 8 into that will give me 8x plus 16 equals 2. Now it's fitting that particular shape, so I can go therefore 3 to the exponent 2 equals 8x plus 16. Right, now we know that 3 squared is 9 equals 8x plus 16, which means 8x equals 9 minus 16. That means, now notice what I'm doing, I'm spinning it around because maths you can read left to right or right to left, equals 9 minus 16, which gives me minus 7. Now if that worries you, rather do that step first and then swing it to that. But I don't think that's a big problem. I'm sure you're comfortable with that. Divide by 8, and your x is equal to minus 7/8. Now remember what I said to you. We have to go back and check that it caused no problems on the restriction. Now, of course, we check in the original, because once we've used a law and we've changed adding the logs into multiplying the logs, it's going to be different, and it could make it true when it was clearly false in the very beginning. So we always check in the original to decide whether a solution is possible or not. So going back to this original one, there's no problem with this. We know that's log to the base 3 of 8, so no problem. And here, this could be a problem, because I know that the inside of that would have to be greater than 0. So if I take minus 7/8 and I put it over here and I add 2, do you agree with me that that would be a positive number, and so therefore there would be no problem, and so that solution is valid? Okay, it's nice to acknowledge it in some way, and underlining or highlighting your solutions is never a bad idea. It just helps the examiner. Don't highlight it in dark colors though, because you don't want to obscure your answer, but you'd like them to be able to see just by glancing, there's your nice neat answer at the end. So either underline it or highlight it in a yellow or something that's light. Right, let's look at another question. Question 3, notice it's taking much the same shape as the previous one, but this time we have a minus between them. Now once again, we want to get back to this format so that we can move it from a log to an exponent. So what we do is we say it's log. The subtract means we are going to divide. So it becomes 2x plus 1 divided by x plus 1. Now notice I have put the brackets because the brackets were there. But in actual fact, this line acts as a bracket. And so it would mean exactly the same thing if I wrote it like that. So that means that thing divided by that thing as a unit. So really it's your choice. I personally think that looks better. That looks a bit cluttered. But since there were brackets, I decided to keep them. Not serious. Do you agree with me? It fits that pattern. But hang on a moment. What is the base? The good news, you'll remember when we were working last time, I said to you if nothing is written, we assume base 10. So in actual fact, we could go back up here and we could put base 10 in here like this. But quite honestly, it's not necessary as long as you remember if there's no base, there is a base 10 there. So it's 10 to the exponent 1 equals 2x plus 1 over x plus 1. Right, we're now going to solve this. Notice therefore, again, you see it doesn't reinforce this. If we put equals like this, do you agree with me that this sentence no longer makes sense? Because now I'm saying it equals 10, which equals that. That's not what we're actually dealing with here. So that would not make sense. So please, whatever you do, remember if you have to write anything, a therefore sign is really good. Right, so now how do we solve this? We're going to times both sides by the denominator. So it's going to become that equals 2x plus 1. So that's going to be 10x plus 10 equals 2x plus 1. And so 10x minus 2x is equal to 1 minus 10, which means 8x is equal to minus 9. Let's get a little bit of space going here. Divide by 8, divide by 8. And so x is equal to minus 9 over 8. We are not finished because as soon as we've done that, our next step is to go back and check that it doesn't make any of my logs invalid. So let's go back and remember what I said to you. Whatever we do, we always check back in the original. So we're going to think to ourselves 2 lots of negative 9 over 8 plus 1. Well, we're going to clearly see that's going to cause a problem because 2 lots of that is going to be minus 9 quarters plus 1, which is minus 5 quarters, which actually makes this less than 0, and we know that that means that that's not defined. And here we're also going to have a problem. So in actual fact, this question has no solution because this is invalid. All right, so that's not the end of the world. We can get questions and equations that don't solve. You've seen them before. Even in grade 9, you were doing questions where you did not get a solution that worked. So we're not worried about that. Let's have a look at the next question. Right, this one looks a little bit different, and I'm going to show you quite a useful technique here. And then I'm going to go back to one of the previous questions and show you that you actually could have used this technique on a previous question. So let's go over here to question 4. Right, let's look at question 4. It says solve for x, but notice this time we have logs in each one of these. Before we've had logs in some of them and numbers in others. So this is a bit different, and it's actually quite a nice way to solve it. So I'm going to do it like this, and then I'm going to go back to one of the previous ones and show you that you could have used this technique to solve the previous question. Right, so looking over here, we have a plus sign. Plus sign means multiply, so it's log to the base 5 of x minus 2 times x plus 1 equals log to the base 5 of 4. Now, at this stage, we can see that we have got the same instruction on both sides. It's log to the base 5, log to the base 5. And so therefore, at this stage, I can equate the insides. So I can say that x minus 2 times x plus 1 must equal 4. Now, this is a normal question that we would get in grade 10. So all we have to do is multiply it out, collect like terms, and factorize because it is a quadratic equation. So let's do it. If we times that by that, we're going to get x squared. If we times that by that, we're going to get plus x. That by that, I'm going to get minus 2x. And that times that is minus 2 equals 4. So I have x squared minus x minus 2. And I'm going to transpose that over as minus 4 equals 0. And so I'm going to end up with x squared minus x minus 6 equals 0. Now, of course, this is a good old trinomial, and we can factorize it, x and x, 3 and 2, a minus 3 and a plus 2 equals 0. That means that x is equal to 3 or x is equal to minus 2. Now I know you're thinking to yourself, now hang on a moment, is it possible to have two solutions here? Well, yes, there is, but we still have to do one more thing. Remember what I said to you, we always go back and we check back in the original to make sure that this is not making my log invalid. So we have the answer 3 and minus 2, so let's go back to the original. If I go up here, 3 minus 2 makes it a 1, that's fine. 3 plus 1 is going to be a 4, which is fine, so this one is perfect. If I take minus 2, minus 2 minus 2, whoops, not a good idea. That's a minus 4, and we know we can't log a negative number. So this one is invalid. All right, so that brings me to the end of that question. You can see it might have been that both were valid. It also might have been that both were invalid. But you do have to go back, and remember, you always check in the original statement. Let's go back to the previous question, and I'm just going to show you that I can redo this question using that technique. So let's just get a clear space here, and let's redo it. Now, what did I say? I said, you noticed that there were logs in everything. Now, if I have a look here, there's a log here, there's a log here, but I could introduce a log here. The base is 10, so it's 10 to the 10, basically 10 and 10 there. Remember we said log to the base a of a is 1, so I'm using that kind of thinking. Now I have logs in everything. Now remember what I also said to you. I said to you, I always make sure that I only have positives rather than negatives. That way it takes away the division. So I would go here and I'd say this is log of 2x plus 1 equals log 10, because the 1 in front doesn't really matter. And I transpose that over as plus log x plus 1. That now becomes log of 2x plus 1 equals log, and this plus means multiply. So now I have log of 2x plus 1 equals log of 10x plus 10. Now I've got log to the base 10, log to the base 10, so I can equate the insides. So I get 2x plus 1 is 10x plus 10. And now sorting it out, I'd have the 10x here, transpose that over here as minus 2x. I've got the 1 here, transpose that over as minus 10. So I have minus 9 equals 8x, which means x is minus 9/8. Exactly the answer I got the other way. It is slightly easier. So if you're finding this more comfortable, perhaps go back and try the one before in a similar fashion. But either method is quite accurate and quite correct. It's really whether you're comfortable changing from a log to an exponent, or you're more comfortable working with logs on both sides. Right, back to the question. What did we do? We took this value and we brought it up here. Let's check it the other way this time. I would say 2x plus 1 must be greater than 0, which means 2x must be greater than minus 1, which means x must be greater than minus a half. Now, minus 9/8 is clearly not greater than that, so this must be invalid. Now, this one here says that x plus 1 must be greater than 0, so x must be greater than minus 1, and again it fails. Now, the question is, if it fails just one of them, is it no longer valid? Yes, that is so. So it's just got to fail once, and then we disregard that as a solution. So it doesn't have to fail both, because if one of the logs is not defined, then the whole question is not defined. Right, let's move on. We've done question 4, just showing you that one, and let's look at question 5. This gives us another opportunity to have a look at doing this method, and you can see now already it's all positive, which is very good news. So what I do is I go alongside and I say the base was 2. So if I'm going to introduce a convenient form of 1 here, I'm going to introduce log to the base 2 of 2. Now that means I have log to the base 2 of x plus 2. And over here, this plus sign is going to be multiplication. But before I deal with that, this number in front needs to go back up as an exponent. So it's log to the base 2 of x plus log to the base 2 of 2 squared. That's using the rule that m log to the base a of n is log to the base a of n to the m. So that's where I'm getting that from. So this now becomes log to the base 2 of x plus 2 equals log to the base 2, and now the adding means multiplying, so it's x times that thing, which happens to be 4. So now I have log to the base 2 of x plus 2 equals log to the base 2 of 4x. Right, now at this stage we have an equal sign. We have the base the same on both sides, the instruction the same, log to the base 2. And so now all we have to do is equate the insides of my log. So let's do that. So we're going to say x plus 2 equals 4x. So 2 is equal to 4x minus x. So 3x equals 2, which means x is equal to 2/3. Now remember, we have to check back, and we must check back in the original. So the answer is 2/3. Let's go back there. 2/3 plus 2 will cause no problem. It's a positive number. And this being 2/3 will cause no problem. There, of course, would be no problem with that. So this one is good, and we can include it as a solution. Right, just for completeness, let's have a quick look at what would happen if I had gone the other route, because that is also very possible. I'm just writing the question out, and then I'll move the screen up, and you can have a look and see. Right, so let's bring it over here. The other route would have been to get the logs on one side, numbers on the other. So I would have gone log to the base 2 of x plus 2 minus log to the base 2 of x equals 2. Remembering that that minus there, in terms of logs, mean division. So it's log to the base 2 of x plus 2 divided by x equals 2. At this stage, I would have said this base takes that as an exponent to give me x plus 2 over x. So 4 equals x plus 2 over x. And of course, you can already see that at this stage, we are going to get exactly the same answer as before, because we're going to get 3x equals 2, which means x is 2/3. And checking our solution like we did before would be exactly the same, but you can see clearly the two answers are identical. So that's really good news. We can always work with that, and life is not so bad. Let's look at the next question. Right, now the next question here, they're just going to place your x in a slightly different position, but the rules and regulations that we've been using up till now are still going to apply. However, there's one thing we can do that makes life a little bit easier. We can say, let's isolate our x's on one side, which I think will make this question just a little bit easier. So let's try that and see how we go. If we get to the end of it and I think it hasn't been as easy as what I thought, we'll do the other way as well. Right, so if I look at this, I'm going to say x log 5, and I'm going to bring this over as minus x log 3. And that is equal to log 3 over 5. Now over here, I can see I'm trying to solve for x. So there's an x there and an x there. So let's take it out as a common factor. So we have log 5 minus log 3 equals log 3/5. Now, of course, subtracting logs means division. So at this stage, I could say, well, that means x in brackets log 5 over 3, because remember, subtract means divide, so it's 5 divided by 3 equals log 3 over 5. Now, I divide this side by log of 5 over 3, as long as I divide this side by log 5 over 3. So I get x is equal to this thing here. Now at this stage, you think to yourself, well, what else can I do? But you actually see something which I hope is obvious to you. This is 3/5, and this one is 5/3. Well, we have a way we can get around that. Using our exponents, we can actually use a negative exponent to invert a fraction. I'm sure you remember when we were doing the exponents section, I showed you what I like to call my rule. I'm going to show it to you on the side again, remind you about it, and we can use this to actually make our lives a little bit easier. So let's go and look at it. My rule went as follows. I said if I have a over b to the minus n, it's equal to b over a to the plus n. So let's have a look here, and let's say that this is effectively to the power 1. So if I want to make it 5/3, I could go log to the 5 over 3 to the negative 1 over the log 5 over 3 I had at the bottom. That now becomes minus log 1 is 1 log 5/3, because I can bring that exponent in front using my laws, over log 5/3. And I can see now that that will divide into that, and my answer is -1. Well, you might say, well, you know, Lee, that's really complicated, and I don't know if I'll remember that in an exam situation, which is understandable. So let's show you another plan, because there is another plan here as well. So going back up to this point over here, let's take the screen up to where we're here. Okay, so I'm going to put it on the side here in pink so you can see it. I've got x log 5 minus log 3 equals log 3 over 5. Right, let's show you an option that is another way to do this question. Right, so if I look at it, I could say, okay, well, that means that x is equal to, and I know that log 3 over 5 is the same as saying log 3 minus log 5, divided by this thing which was over there at the bottom again. So it's going to be log 5 minus log 3. Now you can see that that's okay, but the signs are wrong. So we know that if we take out a negative, we can make the log 5 positive and the log 3 negative. And you can now see that in actual fact this will divide into this, and the answer will be x equals -1. I think that one is probably a little bit easier to work with than the first one, but it's really up to you. It depends how well you cope with your exponents. If you cope with your exponents, the first way is absolutely fine. If you prefer to rather use some basic algebra, then the second way is the better way to go. Right, let's move on to the next example. Right, now this one here says solve for x, and you see this, and of course, hopefully you're looking at this and thinking to yourself, well, you know what, I'm not worried about this. This is actually like my finance, and that's exactly the truth. This log section was wholly and solely used to actually work with our finance when we have to calculate a time interval when we're given something. So you can see this looks just like the formula A equals P 1 minus I to the n, which of course would be your depreciation, reducing balance depreciation, in fact, compound. But it doesn't really matter what it is. The bottom line is, how do we work with it? So let's show you how we work with it. Let's get rid of that. Well, we see that the thing we're looking for is actually this x up here. So the first thing I'm going to do is I'm going to get rid of this thing here. To do that, I divide this side by 155,000 and this side by 155,000. So, right, let's pull the calculator up. Let's clear it, and let's go 45123 divided by 155,000, and I'm going to get the answer. And what's nice about this calculator, it gives it to me as a fraction, which is perfectly acceptable. It's going to be 9/31, and that's equal to 1 minus 0.18 to the power x. Now, just for convenience, I'm going to work this out too. You don't need a calculator, but I will do it on the calculator just to be sure we are accurate. So we're going to clear it, and we're going to go 1 minus 0.18, which gives me 41/50. So it equals 41/50 to the power x. We could have written these as decimals if we felt the urge. Now, at this stage, we have a choice of two approaches. The one is to reverse our log definition from an exponent back to a log, or plan B, log both sides. So I'm going to do both of them, and you can decide for yourself what you feel most comfortable with. So if I'm going to pull out the other method, I'm going to say if I've got a to the b equals c, then I know it's log to the base a of c equals b. So this would become log. The base is 41/50. The number is 9/31, and the answer I'm going to get is x. Right, let's pull up the calculator. And you'll see over here you've got a button that looks like this. So now we know that this one is the answer I had in my calculator, so I'm going to be a little lazy. And this one here is going to be 9/31. And we've got the answer 6,2320, etc., etc. So let's make it 6,23. Now that would usually stand for the number of investments. That might be years. It usually is years when it's depreciation. So I'm saying it will take me 6,23 years to get the amount of 155,000 to become 45,000 at a depreciation rate of 18%. But don't get too worried about what it's saying. I just want you to deal with the mechanics of working with this. Let's show you the second way. Right, the second way, as I said to you, is to log both sides. So what I'm going to do is I'm going to go log of 9 over 31 equals the log of 41 over 50 to the power x. Now, of course, if that's an equation and I do the same thing to both sides of my equation, well, there's no problem. So now this becomes log of 9/31 equals, and from the laws, I know that that x can come in front. So it's x log 41 over 50. Now, I need to get x on its own, so I divide this side by log 41 over 50, and I divide this side by log 41 over 50. That will divide out, and so that's my x answer. Right, it's time to pull up the calculator again, and you'll see that it's just different which key I use on the calculator. And to do this, I'm going to use this normal log button over here, not this one here, because I'm working with base 10. So it's going to be the log of 9 over 31, close my bracket, ooh, nearly made a mistake, spacebar out, and then close the bracket, divided by the log of, and I put the other one in, which is going to be a fraction as well, 41 over 50, spacebar out, close the brackets, press equals, and there you can see we're getting exactly the same answer as this one. So it's really a matter of your personal choice, which one you prefer to work with. I quite like the pink one because it's quite simple and you've got a button on your calculator that allows you to do that. But if you feel more confident in the blue one, please go ahead and use it. It's really a good idea. All right, good. Let's move on. Right, let's look at question 8. It says the sketch represents the graph of the functions f with f of x equal to a of x, a to the x, and g, which is the reflection of f in the y-axis, and h, which is the reflection of g in the x-axis. Well, let's start first of all with our f of x. Let's highlight it in a particular color. Here it is. And the first question they ask me is to calculate the value of a. Now remember, they told me that f of x equals a to the x. Now if we're going to solve for that, all we need to know, since there's only one unknown, is 1 point. And we do know 1 point on this graph. They've told me this point over here is 3 3/8. So let's go and work out our a. We know it takes the form of y equals a to the x. So 3 3/8 equals a to the 3. That's going to be 24 plus 3 is 27 over 8 equals a to the 3. And now we cube root both sides, so we're going to get 3 over 2 equals a. So this equation is y equals 3 over 2 to the x. All right, what did they actually ask me? They didn't ask me for the equation, they just asked me for the a. So therefore a is equal to 3 over 2. Now the next question says write down the equation of g. So write down means literally just look at it and give the answer. Now let's go back to the words and remind ourselves. Over here they were talking about g, which is the reflection of f in the y-axis. Right, let's change color pen. Reflection in the y-axis, what do we know? Well, from our rules, we know that xy will become minus xy if it's a reflection in the y-axis. So if we're looking at the graph we've just got here in pink, and we're now looking for this one, which I'm going to highlight in the purple, well, I know that this must be y equals 3 over 2 to the minus x. Now, of course, that we can simplify a bit further. Let's get some space here on the side. we can say, if I've got y equals 3 over 2 to the minus x, from the law that I said last time is actually my law, I taught you that if we have a over b to the minus n, it's going to equal b over a to the plus n. So using that same principle, I can say that's y equals 2/3, turning that upside down, to the power x. So whether I write this one or I write this one, it would be correct. They wouldn't expect me to use one unless they said to me in the words, the equation must be written without negative exponents. However, that wasn't said, so really it's up to you what you fancy to do. Right, let's read on. What does the next question say? So let's just write this down. The equation of g of x is going to be 2/3 to the x. Now, write down the equation of h. So let's go back there. What do they tell me about h? They say, and h is the reflection of g in the x-axis. So let's have a look. Here's our g in purple. Yes, you can see that that is true for h. And what's the rule to reflect in that axis? Well, the rule says xy will become x minus y. So we're going to take this equation and we're going to make it minus y equals 2/3 to the x, which means y is equal to minus 2/3 to the x. Remember, the negative must be outside this bracket, otherwise it depends whether we have an even amount or an odd amount on the exponent, and then it would be positive or negative. So from definition, we've excluded that possibility. So we put the negative outside of that bracket. Right, so we can go over here and we can write down the equation of h, which means h of x will be negative 2/3 to the x. Right, so we've basically got ourselves a clear picture of this. We've worked with our reflection in the y-axis, reflection in the x-axis, and we're about now to go on to the next part of the question. But for convenience, I've put it on a new page so we don't have such a mess on our hands. Let's go there. What is this next question asking me? It says, write the equation of f to the minus 1. Write the equation of f to the minus 1, making y the subject of the equation. Right, so let's first go back to what y's equation was. Y was 3 over 2 to the x. Now, I'm sure you remember that when we were doing inverses, I talked about that if you're dealing with the inverse of a thing, which this is clearly an inverse, by the way, you see there you've got your f to the minus 1, you would swap your x's and y's around. So if you're going to write down the equation of this inverse, you would know it's going to be x equals 3 over 2 to the y. And of course, if we're going to write it in y form, that's not correct. So we need to change it from an exponent to a log to make y the subject. So what we're going to do is we're going to say, right, this is following the formula a to the b equals c. So it's going to be log to the base a, which in this case is 3 over 2, of the number which is x will equal y. And there you have the equation of the inverse. So in the actual working, you would have started over here. To help them, I think I would have set it out like this. I would have said f is y equals 3 over 2 to the x. So f to the minus 1 is x equals 3 over 2 to the y. That helps my examiner to see how I'm thinking. And then therefore, y is equal to log to the base 3 over 2 of x. Nice and simple to write that down. All right, the next question says to me, sketch this graph. Now the good news is we don't have to start from scratch on our sketching. All we have to do is use the points we know about f to actually find points for f to the minus 1. Remember, we know that there's a reflection about the line, and let's put it here in with dots, y equals x. So we know that if this is my pink line here, and I want to reflect about the axis, I know it's going to look more or less like that. And being a log graph, it will cut there at 1, because we know that this is going to be the coordinate 0 to 1. So over here, we know that this inverse will be 1, 0. We also knew this coordinate. We knew that it was 3, 3 and 3/8. So if we use the swapping of the coordinates, this is going to be 3 and 3/8, 3. So it's going to be sort of out here somewhere, 3 and 3/8, 3. And if I draw in the inverse, it's going to look like this. Now what I want to ask you is, can you imagine folding on that line and those two graphs intersecting or lying on top of each other? And I think you can. Obviously this is not drawn to scale, but it gives you a very good idea that that would be the reflection point of that. Right, so we've drawn f to the -1 without having to go to any major working. Now the next question says, what is the domain of f to the -1? Now, you might remember that when we were doing before, I said to you the domain of f to the -1 is actually the range of f. So we could look at the original and decide what the range was and then say that's the domain. But since we've got it drawn, it's not a big problem. The domain, remember we said as well, that a domain and a range would go alphabetically in that order, which means the x and the y is also alphabetical. So domain is the x values, range is the y. So they're asking me about the domain of the inverse. So if I look at that, you can see that the domain would be from 0 to infinity, because do you agree with me that this normal graph here would have had an asymptote here, but in doing the reflection, it would have the asymptote there. So we know it's going to reflect in a different way, so we know it's going to be greater than 0. So when we write this down, we would say x is greater than 0. Or, there's nothing wrong with using interval notation. X is an element of 0 to positive infinity. I think that that's probably easier, but if you prefer the interval notation, there it is. Right, now we're not finished with this question yet, believe it or not. They're still going to ask me one more question, and again I've got it on a fresh page so we can refer to it. Right, it says here, if h is shifted so that its y-intercept coincides with the origin, what is the equation of this new graph? Well, first of all, let's just extend this axis a little bit. I didn't do too good a job of that, but let's just move it over a little bit so it looks a bit more realistic. And we know that this equation was y equals log to the base 2/3 of x, if I remember rightly. Let's just make sure, rather than make a mistake. I did write it on, no, I talked nonsense. It's not a log, it's a negative. Good thing I checked. Right, let's go back there. This is going to be y equals minus 2/3 to the x. Now they want to know what's going to happen if I pick this graph up and I move it. So let's highlight it, because at the moment it'll be easier to pick my pink one up. And, well, let's mark in 2 here that this coordinate would be 0, -1. So what they want me to do is to pick this h graph up and move it so that that happens. So what has actually happened to move this black to this pink? I've actually shifted my graph of h 1 unit up. Now how do I get this to move up 1 unit? Well, it's relatively straightforward. It's a vertical shift, so it's y equals negative 2/3 to the x plus 1. Because now, just to check it, we can make sure that if I worked out the y-intercept, I would get 0. So let's do that just to make sure, but I know this is right. Let's take this graph and just check it. Okay, I want the y-intercept. So for the y-intercept, I let x equal 0. And doing that, I'm going to get y equals minus 2/3 to the 0 plus 1. Now we know anything to the 0 is 1. So we get that, and if we work it out, we get 0. So we can see the coordinate would be 0, 0, which is precisely what we were asked to do in the question. They wanted the y-intercept to coincide with the origin, which is exactly what this pink graph is doing. So it's nice and easy. All we had to do is think about the movement, and then remember, if it's a vertical shift, we add the number. Right, are we clear on that? I think it's a lovely question, and it's well worth thinking about this question a little bit because they ask it in many versions of the same thing. And at the end, if we have some time, I'll give you a quick summary to help you focus on that. Let's go to the next question. Next question says, study the curve of the exponential function h. The function cuts the y-axis at p0, 1. So that's the normal place to cut. While the coordinate r is a point on the curve. Find the equation of h. Now, when they're telling me this, what they're doing is they're telling me this is an exponential because it's cutting the y-axis, and it doesn't have a vertical shift, and it doesn't have a horizontal shift, so that's why I can go straight there. Now, all I would have to do is substitute in the coordinate 2 9/4 to solve for my a. So doing that, 9/4 equals a squared. To undo that square, our square root, normally we would pick up a plus minus as an answer. But remember, we defined these as having positive bases. So in actual fact, my a is equal to 3/2. And so this equation is y equals 3/2 to the x. They seem to like these questions with 3s/2s, but they're not bad. Right, let's see what the next question asks. So we find the equation of h. Maybe we could have just for completeness have written it as h of x equals 3/2 to the x. Now it says, write down the equation of the inverse in the form y is. Right, so let's go back up there. And let's use the side here to work because that's always easiest to keep it next to the drawing. So let's have a look. Remember what I said to you, we have to try and help them so they can understand what we're doing. So what I'm going to do is I'm going to go h is the graph of y equals 3/2 to the x. So h to the minus 1, knowing that all an inverse is the swap of x and y, or the reflection about the line y equals x, is going to be x equals 3/2 to the y. Now we're going to change it from an exponent to a log, so we're going to say y is equal to log to the base 3/2 of x. That's the base, that's the number, that's the exponent. All I'm doing is using that formula that I had for changing a log to an exponent and an exponent to a log. Right, so now we have the equation of the inverse in the form, but they asked it in y form, so if we wanted to be really complete, we could say y equals log to the base 3/2 of x. Now it says sketch the graph of h to the minus 1. Be sure to indicate any intercepts with the axes and the coordinate of one other point on the graph. Now we don't reinvent the wheel. We know that if it's an inverse, everything is going to swap. The x's and y's are all going to interchange. So in actual fact, we can use the points we've got for h to draw h to the minus 1. So let's go and do that. Let's pull this question down. We know that this is 0, 1, so we know we're going to have a point here, 1, 0. We know this point, so we know that this point over here is going to be 9/4, 2. And we know that this graph would look, oops, I think I went a bit skew there, so let's just tidy it up a bit. It would go like this. Okay, and if we wanted to put in that dotted line so that we've got a indication of how the reflection happened, we'd see it like this. And let's just lift it up a little bit and bring it in line. Okay, and I think you can see just roughly that in actual fact those two are mirror images of each other about the line y equals x. Okay, right, so that takes care of that. They say sketch the graph of h to the minus 1. We have done. Have we indicated any intercepts? Yes, we have. There it is. And have we shown one other point? Yes, we have. There it is. So the question is complete, relatively straightforward. In fact, a lot easier than the first question we did, but clear how to work with it. So right, let's move to the next one. The next one says f of x equals 1/3 to the x. Now at this stage I'd like to just stop for a few seconds and do a little bit of recapping on our graphs. We did mention this before, but I just want to make sure it's in place. And the first thing we did mention that is if a is greater than 1, the graph is increasing. If a lies from 0 to 1, it's decreasing. In other words, if we're thinking of our graph, let's just put a little mini axis over here. Oops, I shouldn't have used that one. let's go to this line rather, a mini axis over here. And I'm saying to you that a is greater than 1. I know this exponential graph would look like that because it would increase in value. On the other hand, if a lay, in fact, let me not put it quite as far over as that. If a lies between 0 and 1, it would be a decreasing function, so it would look like that. Just some information, we know that the domain of these two graphs would be the same. It would be minus infinity to plus infinity, and the range would be from 0 to plus infinity, or y greater than 0. We would have an asymptote in the same place for each of these graphs. So let's go here. We know that this is a third to the x. If it's a third to the x, we know it's going to be a decreasing function. So it's going to be like my blue version of this particular thing. Now it says determine f to the minus 1, writing your answer in that form. Good news is they haven't asked me to draw it yet. They probably are going to, but not yet. So all we're going to do is use our basics of how we deal with an inverse. And we know if we deal with an inverse, xy becomes yx. Right, so over here, remember what I said to you, a good idea is to help your examiner. So to tell them that's my f, and so my inverse is going to be x equals 1/3 to the y. However, they want me to write it in that format, so I must go y equals log to the base 1/3 of x. So it's going to be log to the base 1/3 of x. Right, so it's in the right form now. We have no problems with it. Let's go now to the next question, which says state the domain and range of each of the functions. Now, again, we haven't drawn it yet, but we know, as I just pointed out to you, that the domain for the original will always be minus infinity to plus infinity, and the range would be 0 to infinity or just greater than equal to 0. So let's use that, and then we can, from there, deal with f. So let's work with f in the blue, and let's deal with domain, which is a normal graph, so we know that x is going to be an element of minus infinity to plus infinity. The range, it's a normal graph as well, and y is going to be an element of 0 to plus infinity. Now, if I decide to give the inverses version of this, remember what I said to you, the x and the y are swapping around, and so the domain and range swap around. So the domain of this one is actually the x range, so it's x an element of 0 to infinity, and this is y an element of minus infinity to infinity. And now it says sketch the graphs of f and f to the minus 1 on the same axis and labeling the graphs clearly. So of course that's meaning showing where it cuts the y-axis, making sure they can distinguish f from f to the minus 1, and perhaps showing one other point just to get the accuracy. So let's have a look at it. Right, let's look at this question. It says sketch the graphs of f and f to the minus 1 on the same system of axes, labeling the graphs clearly. That means when the examiner looks at it, they must be able to tell the difference between the original and the inverse, and they must have it clearly marked where it cuts the axis, plus say one other point just to be sure. Right, so let's get ourselves a little axis going over here. How do we draw this kind of graph? Well, we usually sort of table method it almost. Let's just mark the axis clearly. That's the y-axis. This is the x-axis. This is the origin. And we're looking at this particular situation here. So we are drawing f, which is the graph of y equals 1/3 to the x. Right, so if we go over here, if we try the obvious one, which is the y-intercept, and we let x equal 0, we know it's going to cut at 1. So that's definitely a point. We need 1 or 2 more points to make it really work. So let's do x equals minus 1, and if I do that, y is equal to 1/3 to the negative 1, which is going to be 3 to the minus 1 to the minus 1. Let's get it a bit higher, which is 3 to the 1. So we know that at negative 1, we are going to get the answer 3. Negative 1, 3. And if we wanted to, we could go and work out this one, which will be 1/3, but 1 point is enough. So there we have our f drawn for us. Now, we're not going to reinvent the wheel when we get to drawing the inverse. we are just going to reverse these coordinates. So we're going to look at this and we're going to say, instead of cutting the y-axis at 1, it's going to cut the x-axis at 1. So let's plug that in. There it is. Then we know that this coordinate minus 1, 3 could become 3 minus 1. There it is. And we know that this graph is going to look like that, which is f to the minus 1. And I think it's very clear that my pink one is one of the graphs, my black one is one of the other graphs. It's not a bad idea to use colors in exams. Just be careful. You're not allowed to use a green pen or red pen. Red pen's for the marker, green pen's for the moderator, and they don't want to see those two colors. But if you find a purple pen or blue and black, it's fine. You can actually use different color pens to do your graphs in. Also remember, you may not work in pencil. Pencil is a problem because, first of all, if the paper's been stored, pencil's inclined to rub off, and that means that sometimes it's not clear to actually read the question. So just remember to read your instructions clearly and be careful not to do that. Right, the last question here says, find the value of x for which f of x equals 27. Now f of x, remember, is 1/3 to the x, and I want that to equal 27. So in actual fact, what question D is doing is it's asking me to solve an exponential equation, which, as we know, is not a problem. First of all, we'd look at it and we'd say, is it possible to get the bases the same? And the answer is yes. 1/3 is 3 to the minus 1, and 27 is 3 cubed. And so we don't have a problem doing that, so let's do that. So it's 3 to the minus 1, all to the x, equals 3 cubed, which means 3 to the minus x equals 3 cubed, which means then that minus x equals 3. So x is equal to minus 3. Good, so that was easily solved, no problem at all with that, and quite simple. If it had been a question where they were not both possible bases of 3, then we have logs that enable us to solve that. So we don't have a problem whichever way we go. It's always possible to solve that. Right, let's move on. Now we get to question 11. Question 11 says, given the graph of f of x equals 2 to the x, write down the equation in each of the following transformations in the form g of x equals. Now the first one says f of x is shifted 1 unit downwards and 3 units to the right. So let's go back to this original equation, write it down. We have f of x equals 2 to the x. We want to find a new graph, g of x, where this happens to it. Right, so let's pull this down and let's highlight this graph because we're going to move it around and show what happens. Right, let's pick it up. What are they telling me? It shifted 1 unit downwards. So 1 unit downwards is going to bring it there. And then it shifted 3 units to the right. 1, 2, 3. So that's how my finished product for g of x would look. Now, of course, that didn't help me find the equation, but it helps me to orientate myself in terms of what I remember from curve sketching. And what do I remember? I remember if there's a vertical move, the vertical move is a plus or minus on the end. Now, this one was moved down 1 unit. So when I go to find my g of x, I know that this is going to be 2 to the x. That's still going to have things happen. We'll put them in a moment. But I know I must make this minus 1 to get 1 unit downwards. Then the 3 units to the right, remember we talked about this, that the graph actually moves the opposite way to the sign. So if it says 3 units to the right, the sign must be negative in order to move positively. Very illogical, enough to scare anybody senseless. But it actually works and conforms always like this, so it's not a problem. So all we would do over here, 3 units to the right, we would go minus 3. And that would give me my new g of x for this particular graph. All right, I think that's clear enough. This next one, the inverse of f, well, that's not a problem for us, is it? Because we've just been working with inverses. We're feeling comfortable and reassured with it. So let's bring it back to its normal form and then deal from there. Let's bring this back into its position. And let's just label this so we know this was actually A we did. Actually, number 1, not A. Okay, in fact, I think I'm going to put it here rather. G of x equals 2 to the x minus 3 minus 1. Right, let's just tidy that up then because we don't need it there anymore. We just need that one. And now we are working with the inverse. So let's make it in pink. Remember how we worked it with the inverse? We went over here. We know that it's going to be symmetrical to this line. We also know that if we're going to work with the inverse, it's a matter of swapping our x's and y's around. So at the moment, f is y equals 2 to the x. So remember what I said to you about helping your examiner to see what you're doing. Our f is y equals 2 to the x. So our inverse of f will be x equals 2 to the y. Therefore, y equals log to the base 2 of x. Using our rule that a equals b to the c is log to the base b of a equals c. Now looking at that, all I have to do is write it as g of x. So g of x is equal to log to the base 2 of x. And that takes care of that one. Right, the last one says to me, the reflection of f of x in the y-axis. Now we've already dealt with this earlier on, so you should be feeling pretty comfortable with this at this stage. Right, in fact, let's show you, before I go on to that, let's quickly talk about this inverse. So what's going to happen here is we literally, oops, it's decided to give me a hard time here. We literally decide to pull this down. Oh no, not that, this one. No, I think I must give up peacefully with this one. It's decided not to be nice to me at all. Let's maybe use this little rotation thing. The inverse thing would go like this, and it, oh, wrong thing. It would pick this blue one up and it would slide it into that position. And again, it's not perfect because I've just, of course, had to turn it upside down so it hasn't looked too good. But that's how we get it because we're reflecting in the line y equals x. Right, so let's undo that and get it back into its normal position. There it is. And we're ready to go for the last question. The last question says to me, let's use the purple pen, the reflection of f of x in the y-axis. Now, as I said to you, y-axis is not a problem. We have learned to reflect in the y-axis. Our xy becomes minus xy. So all that's going to happen to my graph of f of x is the sign of x will change. So over here, we would say g of x equals 2 to the minus x. Now, this is the same as saying a half to the x. But I think that's easier to understand what's going on. So picking up our equation like this, and I think we're going to probably, let's try and use this method. I'll try one more time, and if I don't get it right, we'll, oh no, it doesn't want to know about my troubles. Okay, let's give up peacefully while we're ahead, and I'll just draw it in freehand. There it is there. And you can see that would be reflected in the line or in the y-axis. So we're clear, it's quite simple, not a problem, and we've sorted it out. Right, so that takes us to the end of that question. Right, now I've got a nice blank page here, and I'm just going to give you a very quick summary of what we have learned to do with logs and exponent graphs. Let's get ourselves a basic axis going. I always do this. I decide to use the dotted line instead of the solid line. Let's just go back there, the solid line. There's the y-axis, there's the x-axis, and let's label them. Now, what we did do is we started off by working with y equals a to the x. If I want a reflection in the x-axis, we know we are going to change the sign of x. So x-axis, and let's call it a reflection so we're clear. So we're going to change the sign of y, so it's going to be minus y equals a to the x. Therefore, y equals minus a to the x. All right, it wouldn't have mattered if I'd had an exponential graph or a log graph. So let's pop a log graph alongside this. Let's put in another axis over here just so you can see. There it is. And let's just pick that up because I see I happily put an extra line in here, cut it off. And let's put a log graph in. So let's put the log graph looking like that. All right, now if it's y equals log to the base a of x, and once again I'm using symmetry here, then I know that what would happen is the sign of y would change. So that's minus y equals log to the base a of x. which means then that y equals minus log to the base a of x. And you might remember at one stage I actually did show you that a minus there can be integrated into that by doing the following. We can say it's y equals log to the base 1 over a of x. But it's not necessary to know that, it's just interesting. Right, let's look at the next symmetry. Let's change to the blue pen. Let's do symmetry about the line x equals 0, or if you like, the y-axis. Okay, now to do that, we change the sign of x. So reflection in the y-axis. Well, if I'm dealing with this graph, it would be as simple as saying y equals a to the minus x. And if I'm dealing with this graph, it would be y equals, the original being that, log to the base a of minus x. Now you might be saying to me, but hang on a moment, that's a bit confusing. How can I have a negative on my x? Well, think about it. If I'm reflecting here, that's my graph. And so what do you notice about these x values? They are negative. So the negative in the front makes the negative of the x become a positive, which means it's still possible. So it makes perfect sense. Right, let's look at the last one, which is the symmetry about the line y equals x. Let's put it in both of these. Okay, and this is just a nice, neat little summary to put it all into perspective for you. So reflecting, let's just get some more space. In y equals x, well, if the original was y equals a to the x, the new one will be x equals a to the y, which is y equals log to the base a of x. And over here on this one, if I'm doing the same reflection, this is like log to the base a of x equals y. Well, now that would become, according to this, it would become x equals log to the base a of y. And of course, y is not the subject, so a to the x equals y. And you can see that these are interchangeable, which of course makes perfect sense. And we can always get around this problem without any real issues. So that gives you a very, very nice little summary. One more thing I want to do with you before we're out of time and show you a little bit more on our actual logs. It's going to take me 2 seconds to just show you this. I don't think it's really that important, but just in case the teacher decides it's a good idea to ask this. Right, so let's just do this one more example just to show you how it works. Sometimes what they will do is they'll say the log of 2 is a and the log of 3 is b. And they'll ask you to evaluate in terms of a and b. Some logs. So for example, say the log of 18. Now, what the object of the exercise would be is for you to change 18 into 2's and 3's, because if you do, you know what they are. So what you do is you look at 18 and you say, let's prime it. Well, I know that 2 goes into 18 9 times, 3 goes into 9 3 times, and 3 goes into 3 once. So this is replaceable with a log of 2 times 3 squared. Okay, I could have written 2 times 3, but that's a little bit more concise. Right, now, what do we know about multiplication? We know that in logs that means addition. So we can go along and we can go log 2 plus log of 3 squared. And of course, in terms of logs, now we've got no problem with this one because we know over here that the log of 2 is replaceable with a. So we can go a plus. Now this 2 is a problem, so we have to bring it in front using our laws. And then once I've done that, I now see I've got my log 3, which means I can replace with my b. Right, so that means I've now got a plus 2b. Very simple, very straightforward, nice little question because it gets you to use your rules in reverse. Now, they can make it a little bit more complicated, but not hugely so. The first complication they're very likely to do with you is the following. They would say to you, evaluate with, in terms of a and b, the log of, let's make it 1, 5. Now, as soon as we see a decimal, the first thing we're going to do is make it a fraction. So we're going to go log of 1 comma 5 is 1.5, or if you like, 3 over 2. Once we're here, it's easy because we know division in logs means subtraction. So it's log 3 minus log 2. And the log of 3 is b, and the log of 2 is a, and we have finished the question. The very last trick they can pull on you is this one, where they ask you to find the log of 5. Now, log of 5, bad news, you can't say 3 plus 2 because there's no rule that allows you to say log of 3 plus 2 is equal to something. And they are banking on you doing just that. So what you're going to do instead is you're going to look at this and you're going to say, well, what can I do? I can't use, it's not going to help me to go, well, actually it is equal to, but not going to help me to go log 3 plus log 2 because I don't have a rule for that. So I have to find another way around the problem. And this is where 10 comes in very, very handy. Because we could write log 5 as 10 over 2, which means I'm dealing with log 10 minus log 2. Now, I know you're saying to yourself, but hang on a moment, I don't know what log 10 is. You actually do. Because remember, the base of this is automatically 10, and anything to the same base in number is equal to 1. And so it will become 1 minus a. So log 5 can always be sorted out by using 10 over 2. Of course, if I'd given you log 5 as an a, say, and asked you for log 2, you could have said 10 over 5 and got the 2 that way. But it doesn't really matter. It's just useful to know that that log 10 is never problematic. Right, this brings us to the end of the section, and I feel we've really done well on our logs and our equations and on our graphs. I feel like we've got those very much under control. I think you've got a clear indication. So thank you very much for joining us today. I hope you enjoyed your lesson and look forward to seeing you next time.